Hello, in this video we're going to do 1.7 periodic trends, specifically 4 of these: atomic ionic radii, ionization energy, electron affinity, and electronegativity. So in the last lesson, we're talking about this idea called the shielding effect, that the electrons have this shield around them and they get blocked from this attraction from the outside, from the nucleus to the outside electrons. And so the electrons they're further away, usually spend less time away from the nucleus, are considered to be shielded because of this inner core of electrons. So if you think of it this way in terms of shielding, what you're really talking about is the idea that the outside electrons are easily reactive because of the fact that they're not attracted to that nucleus. And so this shielding effect is really caused by a couple of things. One is the repulsion from the inner electrons, and also the fact that they're further away. So the inner electrons tend to kind of have this repulsion because they're the same charge as some of the other electrons, and because of that, they tend to kind of kick them out a little bit. And so the way we define this idea of nuclear charge is we have to figure out the effective charge by an electron minus the shielding constant. So if I actually tell you what's the charge of an electron in reality, even though we have the atomic element, let's say, for example, carbon has a proton number of 6, you definitely have a 6 number in there, you still have to take into account the shielding constant. And so the reason why we have this is because the repulsive forces that are caused by this shielding effect really reduce the nuclear charge experienced by the outer electrons. And so you do have a lot of nuclear charge in the middle because of the fact that it's already occupied by these electrons. And on top of that, you have a shielding effect. And that's the reason why these outer electrons tend to really react very well with other elements because of this shielding and nuclear charge issue. That brings us to periodicity. And when you're taking a look at predicting chemical trends and physical trends, we can always look at electrons. Electrons are the ones that define how the changes in chemical changes and physical changes move across or down a period. And this comes down to 5 ways: atomic radii, ionic radii, ionization energies, electron affinity, and electronegativity. I'm going to talk about each one so that you're better familiar with each one there. So let's talk about atomic radius quickly. Atomic radius generally increases from top to bottom. So at the bottom, you have a lot of the larger elements. However, it shrinks or goes smaller from left to right. And this has a lot to do with the fact that we're talking about these electrons and this radii. So when you're going down a group, you're adding new shells. In other words, new quantum numbers. And these are going to have larger orbitals. So for example, if you take a look at something like a lithium or a sodium and so on, as you're going down the group, you are increasing those orbitals. The valence electrons have more energy, and because of that, they're less stable. And because they're less stable, they end up reacting a lot further. And so usually what happens is that as you go down a group, the reactivity increases. The outer electrons have greater shielding, and they have a lower effective nuclear charge, which means that because they're so far away from the nucleus, they end up not being very reactive. They're not really attracted to that center. And so if you take a look at Coulomb's law, what Coulomb's law really comes down to is this idea that you're going to have a force, and that force is really a function of the distance, d, and the actual charge from those electron or proton charges. Now, when you go left to right, it gets a little bit more complicated because even though they are in the same shell, the shielding is really similar to the fact that because you're going from left to right, the proton increases, the proton charge increases. And so as you're increasing the proton charge, what you're really doing is that you're increasing the effective nuclear charge on those electrons. In other words, you're really causing an attraction that's a lot greater as you're going left to right. And so if you take a look, for example, boron versus fluorine, you're increasing the nuclear charge, and you're also increasing the atoms, the number of electrons, but what you're not doing is increasing that distance. And so this specific case really has more to do with the fact that even though you're increasing outer electrons, you're actually not increasing the size of the atom. So as moving left to right, as more protons are being added, according to Coulomb's law, you're increasing that positive charge. In other words, you're increasing that Q value. And because you're increasing that Q value, the force of attraction increases, which means you're actually decreasing the radius. And so that's the reason why you're getting this situation here, where when you're going left to right, the radius actually drops because of the fact that the charges are actually increasing. Now let's talk about ion formation. So metals generally are going to lose electrons to form cations. So if you take a look at K and you form K plus, what you're going to end up with is K plus E minus, right? So this is due to the fact that it's lost in electrons. Nonmetals, when they gain electrons, they form anions. So we already kind of know that. So on the right side of the periodic table, those are usually your nonmetals. The left-hand side, you have your metals, and those are cations. And so when we're talking about your metals, obviously the majority of the periodic table are going to be metals. They like to give electrons. The ones on the right-hand side are usually going to be nonmetals, with the exception of hydrogen on this side, which tended to be, in group 1. They are the ones who accept electrons. And so you're always going to have metals combining with the nonmetals to form new elements. And so for the most part, ionic radius is really driven by its size, how far off those shells are. So potassium as an example, potassium is 227 picometers. This basically represents that it has 4 shells. It's a pretty large, atom. But if potassium loses, the 4th shell, then it shrinks down to 133, which means that it becomes a K+. So as you can see, ions, positive ion charges, are generally going to be smaller than your neutral ones. And take a look at strontium. Strontium has 215. It's a 5 level for strontium. And what happens there is that it's 215 picometers. But again, if I lose that shell, it shrinks down to 127. So ionic radius is really defined as how much of those shells have been lost. Now let's take a look at when you're adding in electrons. So chlorine and chlorine minus, you're actually almost doubling it up. And when you're having O and 2 minus, you're also kind of doubling it up because of the fact that you're adding these extra shells to it. Now, when you're going down a group from top to bottom, the new shells are added. And so as the atom gets larger, you're adding these principal quantum numbers. And what happens here is that the valence electrons have more energy. They're less and less stable, and they're usually further away from the nucleus because of the fact that you're adding in more of these shells. The outer electrons experience greater shielding and decrease nuclear charge, which decreases the force of attraction according to Coulomb's law. So Coulomb's law really is the main idea of why is it the radius is smaller as you go left to right, and why it increases from top to bottom is because of the fact that you're adding more orbitals, and you're also decreasing that attraction as you're expanding those shells. Now, left to right, the radiant of cations decreases. So as you're giving off electrons, the radius decreases because even though you have the same number of electrons remains the same, you're adding more protons from left to right. And so what happens there is that, as you're adding more protons, what you're really doing is that the shielding effect will be very similar. However, by increasing that proton charge, you're actually pulling those electrons a little closer to the nucleus. So that's why in Coulomb's law, the increase in positive charge increases the force of attraction if you're going from left to right. So again, make sure you understand this difference between top to bottom and left to right. Left to right, what you're really doing is that you're increasing the proton charge, and you're increasing that attraction between the proton and the electrons. That's why the radius is smaller. Now, for the anions, it's a little different story if we go left to right. If you actually have an anion, the radius increases very high. So, for example, chlorine and fluorine and all those guys, as you're adding more electrons in, the electron cloud begins to expand. But, however, the radii eventually begins to decrease because of the fact that you do have a shielding effect by outer electrons of the anions in the period. And so even though you're increasing the proton, obviously the electrons are going to have to deal with that attraction as you're increasing the proton. And so according to Coulomb's law, the increase in positive charge increases the force of attraction experienced by each electron, thereby decreasing the radius. So even though you are taking in electrons and you make that cloud larger, the fact is you're also increasing the proton charge, which kind of balances things out a little bit. So going back to that idea of ionization energy, so again, how much energy it needs to remove electrons, you always need electron to remove an electron, energy removed to an electron. And because of that, we see a general pattern. So as you increase levels, reducing the level of valence electrons as you're going from bottom to top, you are actually increasing the amount of ionization energy because they have less electrons to give away. If you're going left to right, you're actually increasing ionization because you're increasing those protons. So protons really are what's driving the left to right pattern for ionization energy, while the energy levels are driving that price to pay up and down a group. And so just generally going back to this idea, it makes perfect sense because if you take a look at the ionization energies of each of these orbitals, you will find that, as you're going in those groups, you'll see this pattern. And so going back to first ionization energy, according to Coulomb's law, the force of attraction decreases as the distance between the electrons and protons increase. So in other words, they are farther away, so they don't really need that. And so the idea is that there's a couple of exceptions, is that it requires more energy to pull an electron from a full D shell than it does to pull an electron in a P subshell. And so again, just kind of read these exceptions really carefully, that it does take more energy to pull electrons from a full subshell than it does to pull an electron. So the answer here is a single electron is easier to remove as it's the only electron in the higher energy sublevel and is being shielded by electrons in the lower energy. So usually a full subshell is very difficult to peel off than, let's say, one electron in a P subshell. Same thing with the D full versus one in the P subshell. So again, going back to the idea of lithium, sodium, all those guys, why they're so reactive, is because those electrons are easier to remove. Second ionization energy is always going to be higher. So after an electron has been removed from one of the shells, to remove a second electron, it requires way more energy. And so what happens there is that the radius is reduced, and then that first electron is removed, but then you start seeing that ratio kind of change a little bit. The ratio of protons to electrons eventually increases. So as you're removing electrons, your protons charge is still the same. So what you're really doing is you're attracting more of that electron that's left over. Every element has one very large increase in ionization energy. So no matter what it is, even if you were to pull off an electron, what happens is that as it drops those quantum numbers, you're actually going to need more energy to remove those extra electrons out.